Well, welcome to Wellness. This is Dhruva from Random Team. Today we are going over Maveric RADP introduction. RIC stands for ML Assisted Virtualized Efficient RIC. RIC as in RAN Intelligent Controller. As we all know, it is a part of ORAN and defined by ORAN Alliance. There are two flavors of it: non real time RIC within the SMO and near real time RIC for OCU ODU for control over CUDU functions. And Linux Foundation has formed a new umbrella organization called as LF Connectivity. It was created as a community to improve connectivity and network access through open source. As of now, there are three foundational projects under LFC. Maverick is one among them. Maverick is the source of RIC Algorithm Development Platform, which enables the development and evaluation of control policies that optimize cellular network operations before their deployment on the network. It is a developer platform that leverages AI/ML approaches, and it provides realistic cellular network representations, also called as RAN digital twin, which enables the optimization of RIC algorithms. The applications and benefits of Maverick are many, and the important things are that with current networks adopting to CI/CD ECT technologies for deployment of RAN software, that is continuous integration, development, and testing, RAN features are needed to be tested in realistic environments before they can be deployed, and Maverick plays a huge part in that. The representation of commercial networks can be hosted in lab environment to enable testing and optimization of RIC operations itself prior to their deployment. RIC operations as in X and RAPs, which are done by third parties. Maverick has also implementations of simple X and RAPs that will demonstrate its use case. Maverick contributions to LFC includes prototypes of ML model that can be trained with data from commercially deployed RAN networks, and it can be integrated into commercially deployed RAN simulator platform apart from the above uses. Let us now look into the architecture of RIC Algorithm Development Platform. Here, the important module is digital twin or digital twins. This is machine learning supervised regression learning models. The digital twin provides a way to use large amounts of data that network operators and vendors have access to train and create network representations and models of aspects such as RF propagation, user mobility, or traffic and load, etc. And these trained models can be then used to generate relevant metrics as shown here. We can consider non-real-time problems such as CCO and energy savings, and near real-time problems such as MRO and MLB. CCO stands for coverage and capacity optimization, and MRO is mobility robustness optimization. MLB is mobility load balancing, all of which the developers try to solve with various algorithms on X and R apps, which are notified here. And these X apps are third-party application entity at near real-time RIC, and R apps are non-real-time RIC entities. Developers can use the RADP in lab environment, and it can be used to evaluate how the solutions are providing policies, RRM parameters, configurations or reconfigurations, etc. This is done in an offline manner without intervening the network. So this is the use case and deployment scenario of this is a typical flow which is available. From the network, we will receive the infrastructure's logical configurations and KPIs. This need not be in real time, it can be provided by collecting it over a period in bulk. The digital twin is realized as a Docker service and can be continuously trained, and it will become available for applications, XApps or RApps, to leverage and like as shown in 4, 5 and 6, it can be leveraged by the applications. Apps can feed the configuration to digital twin, and it can ask queries to generate results with these hypothetical configurations, and this can also be done in loops, and it could be used to evaluate before suggesting the actual configurations on the network. The initial use case that we went through in the previous slide focuses on lab deployment scenario or a developmental environmental scenario. At some point, the digital twin has to be or could be realized as a kernel RAP on the RIC itself to provide live optimization. As of now, this is not implemented, and this is envisioned as the future use case. And so let us continue with the Maveric RADP important components. So the important components that we have taken into consideration here is RADP client and helper, train API, simulation API, QE tracks, and RF prediction. So coming to the RADP client class provides APIs for initiating training of models, simulation, and consumption of simulation output. It acts as a bridge by collecting required data, such as training data and other required data, and porting it into the required format for RADP's API service. And it triggers the HTML request with all these data to a specific API service which is in need or which is being triggered from the application's perspective. And also it collects data or it collects the data of response from the services, and it is again converted to the format which is required by the caller or calling application. And RADP helper, it deals with managing and monitoring of model training and simulation jobs. It waits till the time specified to check if the model is trained, and in case of simulation, if the simulation job is finished or not. So it indicates the status of these jobs. There are two parameters, which is time interval and maximum iteration, with which RADP helper gets us the or indicates us the status of the jobs. Let us look into the train API. Train API allows a user to train a new RF digital twin model. It takes in model ID and it has training parameters, and it takes in UE training data and topology as input. The model ID is an ID which will be used to reference this model in subsequent calls to simulation APIs. The training parameters are the parameters which is passed to training if specified, such as max iter, LR, and stopping threshold. Max iter is the maximum number of iterations to run in training. LR is model's learning rate. Stopping threshold is the threshold for training to stop the training. And we have UV training data and topology, of which examples of them are given here. The training data file will contain cell ID. This cell ID is the identifier of a cell. The RF digital twin will run the training or inference on per cell unit basis. The average RSRP is the RSRP value of this particular cell for longitude and latitude pixel of data which is specified here. And this particular value is the target value for supervised learning employed by the RF digital twin model. And we have cell's EL degree, which is electrical antenna tilt of the cell. And we have topology. Topology is required to enable the model to pre-process UV training data and to create per cell engineered features for training. So it has cell ID, identifier of the cell name as an optional component, and we have cell's latitude and cell's longitude, and we have the cell's azimuth angle degree, and we have cell's carrier frequency layer. For example of these two files, we can follow the path apps and example. Let us delve into the simulation API. Simulation API is used to trigger the simulation task, and for this we input the simulation event object and we input UV data or prediction data, also called as UV tracks data, and we provide config or prediction config. So coming to simulation event, it contains this particular object contains simulation time interval in seconds, and it has UV tracks and RF prediction. So this is the time between the ticks within the simulation. This is the component for the simulation of UV tracks, and this is the component of RF prediction for the simulation. And here we specify the model ID of the trained digital twin. In UV tracks, we will specify UV data ID and key value pair of it if we are passing in the data from a file. If we opt for generating UV tracks, it will contain the UV tracks generation components. So this UV tracks generation and UV data will be touched upon again when we are covering the UV tracks module. So an example of the config is present here. It contains cell ID and cell's EL degree, which is the electrical tilt of the antenna. And this particular simulation API provides us an output which is called as simulation ID. This is the hash value. This simulation identifier is used to consume the output from this particular simulation. And to consume the output, we have an API called as consume simulation output API. With the help of RADP client, we will pass the simulation ID that we got at the time of triggering the simulation, and we get the output. So this output basically is a pandas data frame object. This is pertaining to simulation output. Let us look into the UV tracks now. UV tracks data must be either passed in or it must be generated to run a RIC simulation. The UV tracks key must be present in simulation event object. So while we are passing UV tracks data via UV data file, we must specify UV underscore data underscore ID key as shown below here. In UV tracks, we have this key value pair, and the value that we provide, for example here UV data 1, this will be used to identify this particular UV data which is being passed. And this name that we give here, it need not be the name of the file. And if there are two sequential calls that's been made to simulation API, if it is containing the same value for this particular field, the RADP system will assume the provided UV tracks data is same. So because the system caches the data using hash of this value. So if we wish to pass and run RIC simulation on two different data set, then we must make sure that the names that we are providing or the value that we are providing for UV data ID is unique. Along with adding UV data ID key to simulation object, in this case users must also pass the file path to UV data to RADP client. So now let us look into a sample of UV tracks data. So it contains latitude, longitude of the pixel of data. It is associated with the mock UV ID, which is the fake user equipment associated with this pixel data. And we have tick. Tick is the relative index of this position with respect to time. So for example, if certain mock UID has one position at tick 1 and it has another position at tick 2, this means that the UV has moved from position A to B across a time interval which is equivalent to simulation time interval in seconds. So here mock UID 1 at tick 0 was at this latitude longitude, and at tick 1 it is moved to this particular position. So we can assume that that has happened with the time equivalent to simulation time interval seconds. And we have cell ID. Here in this UV tracks data, cell ID becomes an important thing. So this is the identifier of the cell to attach this data to. So if this column is present, then the RF prediction will only occur from this pixel to this cell. If this column is not provided, then this will occur on per cell basis, where the particular Rx power is outputted for this particular pixel for every cell in the topology file or the topology data. Again, an example of this UV data is present in apps/example path that can be looked into. So up until now, we have learned on how to pass UV data through file or directly as a pandas data frame. So now we can look into generating UV tracks data, since the user has the option to generate UV tracks data with RADP's built-in generation service. So this service employs a Gaussian Markov based mobility model to generate UV tracks. And to UV tracks generation in a RIC simulation, we need to set up the UV tracks object in simulation parameters as shown below here. In UV tracks, we need to specify UV tracks generation, and UV tracks generation has three sub attributes which we have to mention, which is UV class distribution, lat long boundaries, which is latitude longitude boundaries, and Gaussian Markov parameters. So this will be touched upon now in detail. So coming to UV class distribution, this particular object specifies the distribution of UV classes as well as the mobility parameters for each class. The supported UV classes as of now are 4, which are stationary, pedestrian, cyclist, and car. To include this UV class in generated UV tracks, we need to include the class as the key in UV types object with the value of UV type. So for example, in UV class distribution, we will mention pedestrian and car. And for these types, we have UV class params association. So let us look into UV class param. Below is an example of pedestrian and car UV class type with its UV class parameters. There are three basic UV class parameters which are count, velocity and velocity variance. Count is the number of UVs this particular class has to generate in the simulation. Velocity is the average velocity of this particular UV class in meters per second. Velocity variance is the average variance from the average velocity of this UV class. Next we have lat-long boundaries. So the latitude and longitude boundaries of the grid where the UV tracks data will be generated is specified here. So within this particular boundaries we will get the UV data generated, and the UV tracks data will not stray outside of these boundaries that we are going to specify here. Let us look into the Gaussian Markov based mobility. Gaussian Markov mobility algorithm is used for generating UV tracks, and it has certain parameters which are used to tune the randomness of generated data. So the parameters are alpha, variance and RNGC. Alpha is the tuning parameter used to vary the randomness. So we will get totally random values by setting the alpha value to 0, and we'll get linear motion if alpha is set to 1. Variance is the randomness variance of the UVs, and RNG seed is the random number generator seed value to be used to generate the UV data. Here on the right hand side there is a graph which is an example of UV mobility generated using UV tracks generation service for the three particular UVs that we see here. Let us look into the RF prediction module. RF prediction as a component of RIC simulation, users can specify a previously trained RF digital twin model to run an RF prediction. Here, as an input to RF prediction, we need is the data set which is pertaining to UV tracks. Thus, to run RF prediction, UV tracks must be first specified in simulation event object. The field which is required to run RF prediction is just the ID of trained digital twin or model ID of the trained digital twin, which is to be used for the RF prediction. Below is the sample of the output from this module. For the UV tracks data, this step will add predicted per cell RX power data. So below we can see we have UV tracks which is containing cell ID, Mach ID, latitude, longitude, and tick. Associated with it is RX power dBm. So this RX power dBm is the predicted RSRP value in dBm for this cell for the latitude longitude position which is specified there. To install and start the execution of Maveric RADP, this particular link can be followed. So there we can click on code and we can copy the HTTP as clone IP. In a terminal, if we do git clone on that IP, we will get the code base. And in readme.md, there are specific rules or steps that are to be followed to solve the dependencies issues and other prerequisite installations to be done and setting up of environment. Once that is done, then we can start using the Maveric RADP. As part of Maveric RADP's introduction, we are going to cover the test module. The test module helps us in understanding how an RF prediction is run with UV tracks data being passed from a file, and it also has implementation of generating the UV tracks data before the RF prediction. So we will go over that in test module. After test module, there is an implementation of sample or an example app module which will again run an RF prediction with an incremental update approach, and also we can run it without incremental update approach. Those will be explained now. Once we have cloned the Maveric RADP's code, here we'll get this base path. We can go into that. So here we can see we have a test directory and applications directory. The tests path, we have run end-to-end tests and run component tests. In run end-to-end test, there is implementation of happy test cases of RF prediction with UV tracks data being passed in and RF prediction with UV tracks generation implementation. So they have taken the two test cases and here and they have used for loop and they are invoking both the test cases and that is being executed. So the exact implementation of that is present here in the happy test cases folder and we can view this file. In happy RF prediction we have import of client and helper and we have setting up of base path and we have setting up of path for all the input data fields that we need such as topology, training, prediction data, prediction config and model ID is being assigned here. The simulation event object is being read from a file, hence simulation event file path is also taken into picture. Here training parameters are not being used, hence it is an empty dictionary. So initially all the data is being read from CSV format and it is being converted to pandas data frame for all the input data that is being loaded here. Once the data is ready, RADP client and helper are instantiated and the data training is initiated by using train API. After that, with the help of RADP helper, we are trying to resolve model status by waiting for 3 interval and with max attempt of 10. So once the model status is successful, then we are going to proceed ahead and we are opening a simulation event object and we are reading the content for simulation event object and we are triggering RADP simulation with the simulation event, prediction data and prediction config. So we are saving the output of simulation ID here and we are utilizing RADP helper and we are trying to resolve the status of simulation. Once the simulation is successful, then we are going ahead with the help of RADP client with consumption of output for the simulation. We are passing in simulation ID, we are getting the RF data frame and we are printing it. And similarly here in the happy test case of RF prediction with UV tracks generation, we can see that here we are not considering UV data file and in this simulation event file we are using a different simulation event file. In this simulation event file we will have simulation event object which will specify we have to do UV tracks generation, which I'll open and show. Rest everything else is same and we can see that here we are not passing the UV tracks data. So now let us look into the simulation event files. In the example simulation 1, which is for happy test case of RF prediction, we can see that there is UV data ID key and value with the simulation time interval in seconds. And in terms of happy test case for RF prediction with UV tracks data, we can see we have specified that we are going with UV tracks generation and we are giving simulation duration in seconds. And there are classes, stationary, pedestrian, cyclist and car, the count of that particular UV associated with it, velocity and velocity variances. And we have latitude, longitude boundary, we have values added for Gaussian Markov parameters and we are specifying the model ID. And the rest of the data is also present here. This can be looked into. Let us run the tests. The test case is executed. So initially we are running the happy test case with RF prediction by feeding the UV tracks data. So we can see the model is trained, and then we are running simulation, and simulation is done. Results are announced. And when we are running happy test case with UV tracks generation, model is trained. Once the model training is done, we start with simulation. Simulation takes little bit more time because we are generating UV tracks. That means we are invoking UV tracks service. After the UV tracks service has generated UV tracks data, then we are going ahead with simulation. So this is as per the tests implementation. Now let us look into an example app implementation that we have in path apps and example from the base path. Let us go over. So here they have considered two sets of data for training, which is UV training data 1, UV training data 2, and then there are two sets of prediction data, which is UV data 1 and UV data 2. We are working with two of these files, and here we see something called as incremental update, which is set to true. Incremental update is a type of incremental learning, a methodology of ML where a model learns new info over time, building upon the previous one. So if this is set to true, it will have an incremental approach. If it is not set to true, then all the data that is available will be parsed or will be processed at the same time. So now let us look into incremental update being set to true. So we have instantiation of RDP client and helper. Our control will start from here since we have set incremental update to true, and we are training the data model with passing the first set of training data file only. And once the model is trained, that is status is successful, then we are opening a simulation request with only first prediction data file or UV tracks data file. So after that, simulation ID is saved. We are checking for status. Once the simulation status is successful, we are going ahead and we are again training the digital twin with second set of training data. So once the model training is done, next we are going ahead with simulation event file number 2. So the else part will not be executed, hence we can skip that. And now the simulation response is being collected from triggering simulation with both the prediction data files. In the previous particular iteration, we had only considered the first UV tracks. So here we are considering both UV tracks. And from the simulation response, we are saving simulation ID. And after simulation is complete, then we are using it to consume the simulation output into RF data frame, and we are printing it. So let us execute this. Okay. So here we can see we are training the model with the first training data set, and we are running simulation with first UV tracks set, and we are training the data model again with second set of training data, and we are running final simulation with both sets of UV tracks data, and this is the RX power dBm value associated with the particular UV tracks data. So now let us follow the non-incremental update approach. So here what happens when we set incremental update as false is that we will not enter the control of if loop. So let us start looking into the else part. So here we can see we have started the training of data model with both sets of training data, and once the model status is resolved and it is successful, we are going ahead with simulation, and when we are running simulation we are considering both sets of prediction data, and after that we are consuming the simulation output and we are printing RF data frame. So now again let us go ahead and execute. Execution has ended. So here we can see the model is only being trained once and simulation is being only run once, because we are feeding all the data at the same time, and this is the particular RX power dBm which is generated. These two can be compared.